this lecture, we are going to demonstrate deformation tensors, finite strain tensors. Okay, this is ds belonging to the reference or the undeformed configuration. This is ds in the deformed configuration or current configuration. So this is reference configuration, and this is current configuration. Now, ds square is a dot product of dx dot dx, and you know that the vector x is equal x1 e1 plus x2 e2 plus x3 e3. You see, x is related, you see, this is x, this is capital X, this is P0, you see, and this is P. Now this is U, okay? This is the origin. Now, x, the component of x is x1 e1 plus x2 e2 plus x3 e3. So dx is equal dx1 e1 plus dx2 e2 plus dx3 e3. Now, from here, you see ds squared will be, now, dx1 e1 dot dx1 d1. So this will be dx1 x1, because e1 dot e1 is 1, e1 dot e2 is 0, and e1 dot e3 is 0, plus dx2 plus dx3 dx3. But we know that x1 is a function of x1, x2, and x3. x2 is a function of x1, x2, and x3, and x3 is equal, x3 is a function of x1, x2, and x3. So from here, dx1 is equal partial of x1 with respect to capital X1 dx1 plus partial of x1 with respect to x2 dx2 plus partial of x1 with respect to x3 dx3. Now, we can write here using a dummy index, so no problem. You see, this will be partial x1 with respect to xj dxj. J is the dummy index, no problem. This here, we can write dx2 is equal partial of x2 respect to x1, because x2 is a function of x1, x2, and x3, plus this will be dx1 plus partial of x2 respect to x2 dx2 plus partial of x2 respect to x3 dx3. This is partial x2 xj dxj. See, like this, dx3 is equal partial of x3 in respect to x1 dx1 plus partial of x3 x2 dx2 plus partial of x3 dx3. This is partial of x3 respect to xj dxj. Now let's plug this here on ds square. You see, look, ds square will be, now I will write those components here for you to understand, dx1 dx1. So the first dx1 will be partial x1 respect to x1 dx1 plus partial of x1 respect to x2 dx2 plus partial of x1 x3 dx3. You see, this here is dx1. Now I'll multiply, you see, by the same, you see, partial of x1 respect to x1 dx1 plus partial of x1 respect to x2 dx2 plus partial x1 x3 dx3. Now, you see, right here, I'm gonna write here dx1 times dx1. You see? Let's do this. Then after I put dx2 times dx2 and so on. So here we'll have 9 components. So this is equal. Now this, we multiply this, and this. So this will be partial of x1 respect to x1 dx1 times partial of x1 dx1 plus, now this times this. So this will be partial of x1 respect to capital X1 dx1 times partial of x1 x2 dx2 plus, and so on. You see, just for you to understand what I'm going to do. Now let's represent using dummy index. You see, now dx1 times dx1 is equal, now partial of x1 respect to xj dxj. Now attention, now you see, this is 1, okay? Now I will not use j as a dummy, I use I, partial x1 xi dxi. Why am I doing this? Because this is a sum on j. You see, this is a sum on j. It's right over here. You see? And let's this. This is a sum on j. This is a sum on j. But here the dummy could be different from j. Could be k or I or m. Because you see, if I use j here, it's not advisable to use dummy index here and dummy index here, equal dummy index. So use a different one. You see, this could be I, look, I 1 1 2 2 and 3 3. So this will be I here and I here. And over here I can use j. J here. Let's put 1, okay? Just for you to 1 1 2 2, 3, and 3. That's why we use J and J. Just for you to understand why we have to change this index. So let's sum now dx1 dx1 plus dx2 dx2. So here, if you use here, instead of 1, I put 2, here will be 2 and 2. dx3, I put 3 and 3. That's a sum. So I can easily represent the sum using tensor notation. This is dx1 times dx1 is here. Now I'll add dx1 plus dx2 dx2. So here is dx2 dx2. You see, dx2 times dx2 is right here. You see, and over here is dx3 times dx3, dx3 times dx3. And this one is dx1 times dx1. So dx1 times dx1. Not easy. Now you can see now that I could use another dummy index. You see, look, this is 1, 1. You see? Now this is 2 and 2. This is 3 and 3. So we can put this partial of xk, partial xj, partial xk, xi, dxj, dxi. So easy, you see? Because k over here is a dummy. See? A dummy index. Like j is a dummy index, like I is a dummy index. So remember, in our lecture about tensor notation, this is a scalar. It's a scalar quantity. There is no free index. You see here, there is no free indices. You see, because it's scalar. You see, ds, this ds over here, this ds here, this is a scalar quantity. You see, this is a dot product. You see, a dot product, a vector dot product between two vectors are scalar. So this is a scalar. You see, there's many terms. Many terms we can just concentrate, you see, using notation, Cartesian notation. You see, now this we call a tensor, this over here, okay? This is a tensor quantity, let's mark over here. This is a tensor. This is a second order tensor. Now, second order tensor, don't forget, using Lagrangian description. Why Lagrangian description? Because you see the variation with respect to the position vector related to the reference, you see, or the undeformed configuration. You see, this is a second order tensor. Deformation, why deformation? Because you see, we had ds here, capital S, and this is small d. Thus, this is a deformation. This is a tensor, deformation tensor. Now, in terms of the capital X, You see, because capital X is referred to on the form or the reference configuration. See? See, now what you want is not only ds squared, but we want the difference between the deformed length, dx. Now the magnitude of dx is ds squared minus the magnitude of the x, the capital X square. The magnitude of the x, the vector dx is the s. Let's write here. You see, look, dx, the magnitude we call ds, and the magnitude of vector dx you call ds. You see. Now we want this difference for two neighborhood particles of a continuum. This is used to measure the deformation. You see, this deformation occurs in the neighbors of particles between the initial and the final configuration. You see, that's what you want. It's written here. You see. Now let's come to work. Just easy manipulation. You see, ds square is gij dxi dxj. Now gij is a component of a second order tensor. It's called Green's deformation tensor. Don't forget Lagrangian description. You see. Now ds square, I just substitute, you see, this gij dxi dxj over here minus what is ds square. You see, ds is the magnitude of the x, so dx square is dx dot dx. So this over here is dx dot dx. You see, so this dx1 is square plus dx2 is square plus dx3 is square. So I can write this as dxi dxi. You see, I is a dummy index like I did over here. Now you see, I want to put over here dxi dxj. No problem. I use the property of the Kroneck delta. You see, delta ij dxi dxj, you be dxj dxj or dxi dxi. You see, if you don't know, please go in the lecture, see, vector and tensor, and see the properties of the Kroneck delta. That's very easy. So then gij minus delta ij dxi dxj, I call by definition, okay, 2 times this is the Lagrangian. You see, Lij is the Lagrangian finite strain tensor. Lij by definition. You see, it's 2 times the xi this xj. So the second order tensor is defined as 1/2 of. Now attention here is very important. You see, this Lagrangian or Green's finite strain tensor is written in terms of, you see, this over here is don't forget the deformation gradient. You see, gradient. You see, this Lagrangian or Green's finite strain tensor is written in terms of the deformation gradient. You see, do you remember? dxk respect to xi. This, remember, this case, okay? This function, this second order tensor f, you see, is the deformation gradient. We have been done this in previous lectures, so no problem. Now what I want to represent this second order tensor, the finite strain tensor, in terms of the displacement vector components, U. Let's do it. Finite strain tensor, Lij, is written in terms of the deformation gradient. You see, this is the deformation gradient. You see, and now we can represent the second order tensor in terms of the displacement vector, the displacement components, Ui. Remember, we did in few lectures before delta xi plus delta ui, so the derivative with respect to capital Xj is delta ij plus partial ui, partial derivative of ui with respect to xj, and remember that this is the deformation gradient, which we call this as f, and this is the displacement gradient, that partial ui respect to capital, attention here, capital Xj, which means that we are working with Lagrangian description. Now you see, let's substitute partial xi respect to xj, this expression right over here. You see, now you just compare. You see, this is I, this is k, this is j, this is I. So partial derivative xk respect to capital Xi is delta ki, you see, delta ki plus partial uk, partial derivative of uk respect to xi. You see, you look here, and you look there. You see, now you substitute I by k, you see, I by k. And in this case, you substitute I by j. So just right, just easy to see it. Just, you have to pay attention only. You see, here, partial xk, partial derivative xk respect to capital Xj. You just compare here, so I is k. So I is k, and here is j, and here is j. So delta kj plus the partial derivative of uk respect to xj. You just compare here. You see, you move I and put k. You move I and put k over here. And from here, you move and put the I over here. So that's quite easy just to compare. Now let's multiply this times this. Let's develop this. So this term over here, there's a sum plus times this sum over here. So it's delta ki, delta kj plus delta ki that multiply the partial uk respect to xj, partial derivative. Now this times this is this, and this times this is this. It's quite simple. Now attention, let's use the property of delta chronic delta, okay, what we did before. So delta ki, delta kj, you move k and put I, so delta ij. Delta ki, this is k, you move k and put, in this case, put I. Delta kj, you see, you move k and put j. So this is quite simple. We are using the property of the chronic delta, you see? And this is the expression. Now, it will be easy. You see, you substitute this expression right here. And you see, this we have plus delta ij, you see? And this is minus delta ij. So they cancel. So Lij is equal 1/2 of this expression here. You see, this is partial of ui respect to xj plus partial of uj respect to xi plus partial of uk respect to xi, partial of uk respect to xj. See? This is second order tensor. Now, written in terms of the displacement gradient. You see? The other description, you see? The deformation tensor, finite strain tensors. Now we start with the dot product. dx dot dx. This is ds squared. Now dx, capital X, is related to the underformed or reference configuration. You see, there's a scalar product. Now you have to remember that x1 is function of x1, x2, x3. So dx1 is equal partial of x1 with respect to small x1 dx1 plus partial of x1 with respect to x2 dx2 plus partial of x1 with respect to x3 dx3. So this I can write using the dummy index. So this is partial of x1 partial xi dxi. So I is a dummy. Now if I substitute 1 by 2, he will be 2. This 1 by 3, he will 3. So d dxi is equal partial derivative of xi xj dxj. So it's quite simple here. See? Now ds square, you see? Now it's dx1 dx1. So this will be easy to follow this. The same as we did before. So this will be dx, in this case, I dxj. Now, you see, dxi dxj, I will put here delta ij. You see? Delta ij. The same. dxi dxj. Now, dxi dot dxj, now, we're gonna use as we did before. So, you substitute here dx1 times dx2. You see? This times this, plus, now, it will be 2 over here. You see? dx2. So, dx2 plus dx3 dx3. Exactly like we did before. That's a dummy index k. And this is the Cauchy's or Eulerian strain tensor. Now, this is important. Now, pay attention to this. You see, here the derivative is with respect to the spatial coordinates. Okay? Now, from here, we can write the tensor, as we did for Lagrangian, now we did for Eulerian. Now, just quite easy, because we want ds squared minus ds squared. We want this difference. Now, written in terms of Eulerian, the Eulerian description. So exactly as we did before. So ds squared minus ds squared. You see the difference, the square difference. This is dxi dxi. So you see ds squared over here. This is dxi dot dx. So dxi dxi minus, now ds squared, you already did over there. So this is minus, you see, you just substitute over here this ds squared right here, you see. Now you use the Kranach delta ij, that's I, that's j, so it is the same of dxi times dxi. You see, minus, now there's a Cauchy's or Eulerian strain tensor right here. Now let's call these 2 times eij, e as Eulerian, okay? Eij 1/2 delta ij minus these, remember, these, the deformation gradient, the inverse, you see, this is f minus, this is ij, which you call h, you see. This is the partial derivative of capital X with respect to small x. This is deformation gradient, the inverse of deformation gradient. Now, let's substitute, you see, partial sk with respect to xi, partial sk with respect to xj, just for us to represent the Eulerian or Almancy's finite strain tensor in terms of the displacement vector. Let's do it. Delta xi with respect to the derivative of xi with respect to xj, delta ij minus the partial derivative of ui with respect to xj. Now let's change symbols here. So this I want delta xk with respect to xi. You just compare, you see? This here is equal, now k here, so delta k, and instead of j is I, so this ki. Now minus, instead of I is k, so this partial of uk, instead of j is I, so this xi. Okay, the same we'll do with this product here, partial of xk with respect to xj. You see? Now, you just look at here. You see? This I, so this will be delta k. Now, this is j, so delta k j minus partial. Now, this is I, this is k, so uk. Now, x, partial x is j, you see? Now, you just put j over here. Now, let's multiply, you see, this by this. So, let's multiply partial of xk with respect to xi, this times partial of xk with respect to xj. This is equal. Now, let's do it. Delta ki times delta kj minus, now this times this, minus delta ki partial of uk with respect to xj. You see, this here will multiply this, and this will multiply this. Now this minus, now this will multiply delta kj times partial of uk with respect to xi, and then finally plus, now the product, okay, this times this, plus, I'll put here, plus partial derivative of uk with respect to xi times partial of uk with respect to xj. You see, we are adjusting, develop this term over here. So let's use the Cronach delta property. You see, delta ki, delta kj, so this will be delta ij. Now, delta ki, this will be minus partial derivative of, you see, you move k and put I with respect to xj minus delta kj, this will be partial of uj with respect to xi. Now, here, this one, I repeat this one, you see, plus partial of uk with respect to xi, partial of uk with respect to xj. Now, let's substitute, you see, this term over here. But this will have minus sign. You see, minus sign, this will be, I'll put here, see, look, I'll put minus over here, just to, minus here, you'll be, now, you'll be delta ij, I just put minus here, minus, this will be plus, this will be plus, and this will be minus. So, this term over here is just, I will erase here, okay? Erase over here. So, I have, in this case, okay, I will have a erase over here, just, I will leave the last equality, okay? This minus here will be minus here, plus, plus, and minus. So when I substitute here, you see plus delta j minus delta j will cancel. So Eij is equal 1/2 now partial of ui respect to xj plus partial of uj respect to xi minus here partial of uk respect to xi partial of uk respect to xj. So this is the Eulerian finite strain tensor written in terms of the gradient of the displacement. You see this is Eulerian. Okay, look, this is small x over here, you see? So that's the formula.